Another way to calculate the delta H of the reaction is by comparing the cost of breaking bonds in the reactants and the cost, or the benefit, I guess, of forming reaction bonds in the product. So the amount of energy it takes to break 1 mole of a bond in a compound is called the bond energy. It's assumed to be in the gas state, and these bonds are broken homolytically, which means each atom gets half of the bonding electrons. We're just chopping it right down the middle. Now, there are some trends in bond energies. Typically, the more electrons two atoms share, the stronger the bond. And the way you have to compare bonds between like atoms. So a carbon-carbon triple bond has more energy than a carbon-carbon double bond, which has more energy than a carbon-carbon single bond. And that also follows the trend of the shorter the covalent bond, the stronger the bond. And again, we have to compare similar types. So carbon-carbon triple bonds are shorter than double bonds, which are shorter than single bonds. And we can compare things like the bonds between bromine and fluorine, bromine and chlorine, and bromine and bromine. And we see that the bonds are getting weaker as we go down the column, and they'll get stronger across the period, again, because your bond or your atomic radius is decreasing across the period. Like I mentioned, you can use those bond energies to estimate your delta H of the reaction. Your actual bond energy is going to depend on the rest of the molecule, but we can use average bond energies to estimate your delta H of the reaction, and it's going to work best in the gas state. Bond breaking is always going to be endothermic, or a positive delta H. Bond making is always exothermic. And so overall, another way to look at the delta H of the reaction is by adding up all of the bonds broken, which are all going to have a positive sign, and adding up all of the bonds formed, which are going to have a negative sign, to get you your overall delta H of the reaction. So for instance, we can estimate the enthalpy of the following reaction. So here we have methane plus chlorine gas gives us our molecule here and hydrochloric acid. So we have broken 1 mole of carbon-hydrogen bonds. We've broken 1 mole of chlorine-chlorine bonds. So in total, we can use table 9.3 down here to find our average bond energies. So in total, we've used up 657 kilojoules of energy, but then we've formed a carbon-chlorine bond and a hydrogen-chlorine bond, which gets us a total of negative 770 kilojoules given off from our bond forming. And if we add those two together, we get an overall delta H of the reaction of negative 113 kilojoules. So let's practice. I would, again, pause the video and practice yourself. Estimate the enthalpy of the following reaction. So overall, we are breaking 1 hydrogen-hydrogen bond. So that's going to take 436 kilojoules. We are breaking an oxygen-oxygen bond, which is 498 kilojoules. That gives us a total of 934 kilojoules in our bonds breaking side. Then in our bonds forming side, we are forming 2 hydrogen-oxygen bonds, which are 464, plus, and forming it's going to give it off, plus 1 times an oxygen-oxygen bond, which is 142. So in total, we will give off 1,070 kilojoules. And so if we add those together, plus R934, we get a total of 136 kilojoules given off by the reaction of hydrogen with oxygen to form hydrogen peroxide. So, and then you can see how that compares with the delta H of formation from the back of the book is negative 136.3, so it's pretty close. Good way to estimate. Bond lengths, just like atomic radii, we use the average because it's going to depend on what's around it. And bond length is just defined as the distance between the nuclei. And you can see here the more bonds, so single to double to triple bonds for carbon, our bond length decreases, same for nitrogen. So yeah, that's the trend. And then as your elements get bigger, your bond length increases if you're looking at the same other element. Okay, a couple slides on metallic bonds. So metals have low ionization energy that allows them to lose electrons easily. We've talked about that. So in a solid metal, the electrons released go into this shared electron sea, which here's a picture. So the nucleus and the core electrons kind of form these little islands, and then the electrons are able to easily move through the metal in this electron sea surrounding the sodium, in this case sodium ions, which allows for why solid metals conduct electricity, because you have these bands of electrons in there it's an orbital band that can move throughout the metal.